Meeting C++ has been the first conference that I ever gave a conference talk in 2016, so 8 years ago. And so it's like always great to come back here and talk again. This time for like more people than back in 2016. You know, times change. Anyways, this is an incomplete guide to C++ object lifetimes. So essentially, we're going to talk about this part of Hannah's keynote. We're not going to focus on the part of the heap allocations that are leaking. That isn't necessarily interesting. But we're going to talk a lot about the lifetime extension part. So this is a talk about object lifetime. So the first question we need to answer is, what are objects and what is lifetime? Objects are fundamental to C++. And I don't mean objects in the object-oriented sense of the word. I mean objects as a term of art in the C++ standard. So intro.object, paragraph 1, this is a quote of the C++ standard. The constructs in a C++ program create, destroy, refer to, access, and manipulate objects. So essentially, all your C++ program does is change objects. To understand objects, we need to understand three things. The first term is storage, the second term is value, and the third term is type. So let's begin with storage. The fundamental storage unit in the C++ memory model is a byte. And then a program consists of one or more contiguous bytes, and each byte has an address. So here we've got a couple of bytes. Each byte has an address, and I've highlighted the byte in the red square. Right? This contains the bits that make up the hexadecimal value 41. Now, what does OX41 mean? That's the question about the value. What value is OX41? It could be the 8-bit integer 65. It could be the character uppercase A. It could be the start of the string beginning with uppercase A, right? And then we've got more bytes afterwards that make up the value. Or it could be some byte in the middle of a 32-bit integer. Or anything else. So Elements of Programming is another fundamental book about C++. Well, not really about C++, about programming, but it's a really good book. And in Elements of Programming, it gives a really good definition of value. So we've got a datum, and a datum is a finite sequence of zeros and ones. And then a datum, together with its interpretation, is a value. Right? So value is just, we've got a particular sequence of bits, and we're going to interpret them in a particular way to make up a mathematical value. Value is a mathematical term. And now a type. Well, a type is simply the thing that describes how a datum is interpreted. So for example, we have the type unsigned char, and the type unsigned char says we take 1 byte of memory, and we interpret it as an 8-bit unsigned integer. In the type int, we take 4 bytes on most platforms of memory and interpret it as a 32-bit 2's complement integer. Types can be more complex, so in the types.string, we take 24 bytes of memory, and we interpret it as a pointer to a null-terminated sequence of char. Then we've got some bytes that make up a size, and then we've got some bytes that make up a capacity. Right? But the type simply describes how a datum is interpreted. And now what are objects? Well, an object is something that has a particular type. It occupies a region of storage at a particular address, and there the value is stored. So here, int x, we've got an object of type int. It currently stores the value 42. Then float y, we've got an object of type float. It currently stores the value 3.14. And then we can change the value of an object using assignment. So now we change the value of x to 11. Now, it's important to point out what isn't an object. For example, functions aren't objects. Even though functions live somewhere in memory where the executable code lives, the C++ standard doesn't consider them objects. Right? So a function isn't an object, but it's implicitly convertible to a function pointer, and that is an object. And its value represents the address of f. But functions on its own aren't objects. Similarly, references aren't objects. References are simply aliases to other objects. So here we've got one object, x, of type int, and then we've got another name to x as x, ref. It's a reference, it's an alias to the object defined above. Now what is lifetime? Well, lifetime, quite simply, is a runtime property of the object. So objects have a lifetime among the other properties they have, but it's a pretty important property, right? Because all other properties, there are some exceptions, are only valid for an object when it is in its lifetime. So when it is alive. After it has been destroyed, the properties are no longer valid, and before they're destroyed, the properties are no longer valid either. And in particular, there's a footnote that says there are significant restrictions on the use of an object before the lifetime has started and after the lifetime has ended. So lifetime is a pretty important property of an object to understand. So on a very high level, the object lifetime cycle in a nutshell looks like this. Every object needs storage, so first we need to allocate storage for the object. Then we initialize the object. We'll get to the quotes later. And this starts the lifetime. So now we've got an object who is alive. Then we can use the object, we can read its value, we can change its value. When we're done, we destroy the object, which ends the lifetime. This may or may not run a destructor, as we'll see. Then we will deallocate the storage, and then we're done. So like every object in your C++ program goes through all these 5 stages, and the rest of the talk is just going to focus on when the individual points happen. Now some note about terminology. The standard says that objects can be created. This isn't a one-time operation that starts the lifetime. It's something like a declaration. Like a declaration creates an object, and at some later point, the lifetime is going to be started. Confusingly, the opposite, objects can be destroyed. That's the runtime property, which will end the lifetime. And it's a bit of an unfortunate phrasing, and I will probably try and I will try to not, be very precise there, but I might say create in order to mean the runtime operation that starts the lifetime, even though that is technically incorrect. It's also to point out that lifetime is something the standard invented to describe the semantics on the abstract machine. Right? It's part of the formal model of C++. It has absolutely nothing to do with your physical machine. Like your CPU doesn't care about objects, it doesn't care about lifetime. Right? It's purely a phrase or term of art for the C++ standard in order to give it semantics. So with that, let's look at some object lifetimes. And we begin in the very basic level, variable declarations. So intro that object paragraph 1, an object is created by a definition. For example, here we have a definition of a variable x. This creates the object, allocates storage, and starts the lifetime, as we'll see. Then we can use the object, as discussed, and then in the closing brace, the object is destroyed, which ends the lifetime and deallocates storage. And when this happens, this depends on the storage duration, most notably. So storage duration is another property of an object, and it defines the minimum potential lifetime of the storage. And it depends on how we create the object. In our case, for definitions, we care about 3 storage durations, static, thread, and automatic storage duration. So let's look at one, automatic storage duration. This is the most basic storage duration, and it applies to anything that is defined in a function. And there, the storage lasts until the block in which I created exits. So when we are of function main, the first line, this allocates storage of A. The second line allocates storage of B. Then we create another block. This allocates storage of C. When we close the block, this formally ends, deallocates the storage of C. The CPU probably isn't going to deallocate the storage at this point. We're going to do it later. But again, the CPU doesn't care about the semantics. But formally, this is when the storage ends. And then when we end the function, we deallocate the storage of A and B. Then we've got static storage duration. Static storage duration applies to variables with the static or extern keyword. And their storage is a lot simpler. They simply exist throughout the entire lifetime of the program. So here, all those variables have static storage duration, and their storage is allocated before the program starts and deallocated at some point after the program ends. And yes, you can declare a global variable within the function by just using extern. Thread local defines thread storage duration, and that is very similar. Instead of throughout the entire program, it's throughout the entire thread, and there's 1 copy per thread. So we're having a thread local variable. And when we start executing main, we have allocated 1 copy for it. Then we launch another thread. This allocates another copy of the thread local variable. When we destroy the thread, we deallocate the copy. And when we end the program, we will end the lifetime of the main thread. Right? So just like static, just 1 per thread. Now, storage duration is not directly related to lifetime. In general, it's a superset. Right? But storage duration is not the same as the lifetime of an object. Because the lifetime only begins when we both allocated the storage and we did the initialization. So the real question about lifetime is, we've now got the storage, when does the initialization take place? Because that is what we need to know about the lifetime start. For automatic storage duration, it's easy. There's a storage duration and the lifetime match. So as soon as we allocate the storage, we also do the initialization and start the lifetime. It would be weird if it were different. But for static and thread storage duration, it's a lot more complicated. Then you have to look at function local static, where there's global scope, there's const in it, there's dynamic initialization, there are techniques called nifty counters, we have to look at the module dependency graph, and inline variables. I gave an entire talk, apparently, at this conference, the static initialization order fiasco, where I go into the detail. It's another 60-minute talk. So I'm not going to go into this right now, I'm just going to look at all the other cases. But it's complicated. Now, a couple slides ago, I said the lifetime starts when the initialization, if there is any, is completed. Because in general, an object can have its lifetime start without a non-value. Right? So this is the formal wording for that. When we allocate storage, the object has an indeterminate value. And if we don't do any initialization, then the lifetime starts anyway, because the lifetime starts as soon as we did the initialization, if there is any. So if there's no initialization, the lifetime starts immediately with an indeterminate value. And then that object keeps this indeterminate value, and when we read it and get an indeterminate value, we have undefined behavior. So here we've got our int x. It doesn't do any initialization because int doesn't have a constructor. So this allocates the storage and starts the lifetime with an indeterminate value. So this read is undefined behavior because we're reading an indeterminate value. But the assignment is OK. And after the assignment, we're allowed to read it. And this is also why the assignment is OK, right? Because we didn't do initialization. If that didn't start the lifetime, then the assignment would be undefined behavior because there is no object who's alive to do the assignment. But the lifetime starts just with an indeterminate value, and so the assignment is OK. And if you attended the quiz yesterday, you will know that like in C++26, this is going to change. It's no longer undefined behavior, instead it's erroneous behavior. And erroneous behavior is like a weaker form of undefined behavior, where it's sort of like we ask the compiler to please do the right thing. Like, don't optimize assuming it doesn't happen, just be nice to us, and like maybe issue a diagnostic or do some sane behavior, right? So it's like a much tamer version of undefined behavior. But that is variable declarations. It's a big room, so like if there are any urgent questions, ask them now, but like if there are non-urgent questions, ask them at the end in front of the microphone. So let's go with that. Okay. Let's look at new and delete. An object is created by a new expression. And then we've got the corresponding delete expression, which destroys the object. So here, when we write int pointer equals new int, this creates the object, it allocates storage, and it starts the lifetime because we did the allocation of the storage and the initialization. So now we've got an object that is alive. Then we can use the object as before, and then we can delete it. Also note that like the pointer itself is a separate object, right? This is an object created by a variable declaration that follows the rules from the previous section, but like I'm now talking about the int that is created on the heap. And it is also possible to create one with an indeterminate value, right? So if you just like pointer equals new int, this doesn't do any initialization, but it nevertheless starts the lifetime just with an indeterminate value. And so the same rules sort of apply. This is undefined behavior. You have to assign it first, and then it's OK. So that one was even simpler, right? With new and delete, we've got like more control over the allocation and the start of the lifetime. So let's talk about something more interesting, temporary objects. An object is created when a temporary object is created, which is a tautology. Consider this code. We have a function called f, which takes an object which takes a reference to a constant. And then we call it with 42. Now 42 isn't an object. 42 is a number. Yet references are aliases to objects. So we need an object. And so when we do this call, we create a temporary object, initialize to 42, and bind that to the reference. The formal phrase for this is temporary materialization conversion. If you're looking for Hangman, temporary materialization conversion. And the standard says a PR value of type t can be converted to an x value of type t. This conversion initializes a temporary object of type t from the PR value by evaluating the PR value with the temporary object as its result object and produces an x value denoting the temporary object. Somebody was trying to like pad the wording or something. What this is saying is, whenever you use a PR value in a context when x value is expected to create a temporary object with that same value. And those contexts are, we bind the reference to a PR value. References require objects, so we do temporary materialization conversion in order to create an object. When we do member access on a PR value, like member functions have a this pointer. The this pointer refers to an address. Like a temporary, like we need some address there, so we materialize an object. When we use an array really wants to be a pointer to the first address, so again, we need some address, so we materialize the literal into a temporary object. Interestingly, this one, so when we have a function that returns a PR value. So for example, a function std_string f. Then this std_string has a destructor. We want to destroy this destructor when we don't need it. But the destructor is a member function, so in order to do that, we create a temporary object, initialize it to the function call, and immediately destroy it. So that's temporary materialization conversion. The question is, what is the lifetime? And the beginning is easy. When a temporary is created, its lifetime starts. and the temporary is destroyed as the last step of evaluating the full expression that lexically contains it. So consider the function f. It takes a whole bunch of references. And then we're calling it with two PR values, the number 11 and the result of the function g. This causes temporary materialization conversion to kick in and create two objects, one containing the value 11 and one containing whatever is the result of g. And then we execute a function. The function can now freely use the references since they bind to objects, and when we reach the semicolon, we sort of destroy those temporaries. So with an f, it's fine to use the references, but when we store pointers to those objects somewhere else, then we can no longer access them after the call to f because they're destroyed at the semicolon. This is a very simple rule, but as you saw in the keynote, it's not as simple because of temporary lifetime extension. So when we have a reference that is bound to a temporary, then the lifetime of the temporary is extended to the lifetime of the reference. Now, first of all, references aren't objects, so references don't have lifetime. But the standard sort of treats the references as if it were an object, and so and then it would have a lifetime, and that is the lifetime it means here. So, for example, in the first line, we create a reference to a temporary object. This reference is treated as if it has a lifetime that is destroyed at the closing brace. So temporary lifetime extension extends the lifetime of the temporary object throughout the entire function, and so we can use it in the second line. And the idea behind this, since the first line compiles, if the temporary were then destroyed at the semicolon, which would be the case without lifetime extension, then it would be a pretty useless construct, right? Because you can't use the reference at all. So helpfully, quote unquote, we sort of extend the lifetime of the temporary in order to use it throughout the lifetime of the reference. This, however, is incredibly subtle, because the reference has to be a reference that directly binds to the temporary. So consider getStrings. It returns a vector of string, which is a PR value. So when we initialize it in the first line, we bind a reference to a PR value. Lifetime extension kicks in, and it's fine to use strings, because it's only destroyed at the closing brace. However, in the second line, lifetime extension does not kick in, because here we're calling a member function. When we're calling a member function, this is the thing that triggers the temporary materialization conversion. So we have a temporary object initialized from the result of getStrings, and we're calling a member function. This member function, operator square bracket, returns a reference. And then we're binding that reference to the reference in our main function. So at no point do we bind the reference to a PR value, so we don't have temporary lifetime extension. Instead, we just have a reference to the first member of our temporary vector, which is destroyed at the semicolon, and so we immediately have a dangling thing. And temporary lifetime extension is incredibly subtle. So you shouldn't really rely on it. There's a second case of temporary lifetime extension, which is much nicer. All temporaries created within a range-based for loop are destroyed after the loop. So here, we're iterating over the result of getStrings. This is perfectly fine. It's a temporary created in the range-based for loop, and it's destroyed at the end of the range-based for loop. And also, even when we're iterating over the first one, we create a temporary when we do the member access. This temporary is created within the range-based for loop, so it's destroyed at the semicolon. But note it only applies to temporaries created between the colon and the closing, the closing parent, not temporaries within the lifetime in general. Is Nico here? Okay, Nico left. So thanks, Nico, for adding this feature to I forgot which standard it is, and it's it wasn't there before. Nico fought hard to make it in to sort of remove some sharp edge on that feature. So those are temporary lifetimes. Now let's start really messing with things and look at placement new. Back to this quote. An object is created by new expression. There's a special kind of new expression, placement new. Placement new takes some address, some storage, and explicitly sort of creates an object in there by it's sort of an explicit constructor call. So here we're having some pointer to some storage, and we are placement newing an int in there, and explicitly calling and creating an int in there. Now, I use the double colons and the void pointer. This is because you sort of have to call placement new always like this. You have to fully qualify it to get the global scope on, and then cast it to void, because it can be overloaded. And if you don't do that, then you might get the weird overload that does something slightly different. This is a bit annoying. So there's a standard function, construct add. Construct add simply is a wrapper over placement new that does it for you. I'm not going to be using it in this talk because it doesn't fit on the slides. Like you have to do more casts. The placement new one is shorter. But keep that in mind. Either write placement new with the colon and the static cast, or just use std construct add. Now we've manually created an object, and because we manually created it, the compiler isn't going to destroy it for it. So we have to explicitly destroy it as well. And for that, we can use an explicit destructor call. So the syntax for that is object dot tilde and then the name of the type. And there's a really weird quirk about the grammar. The T there, the name of the type, this has to be an identifier, which means that you cannot use that for ints or other built-in types, because then you would tilde int, and int isn't an identifier. It has to be an identifier. It also can be a scoped identifier, right? So you can't write dot tilde string, right? You either have to then use a type def or using declaration, or you instead use the standard version, destroy add. So destroy add takes a template parameter, and then the name of the type is simply t, which is an identifier, and so we can write the grammar, right? It's purely like a syntactical restriction, right? It's not something to do with what sort of semantically you can do it on. It's just the grammar only allows an identifier. It doesn't allow a keyword. It doesn't allow a scoped identifier. So I am going to use destroy add on the slides. So now we know to manually create an object and manually destroy it. How do we allocate storage, right? We need some storage to do that in. Right? And the most obvious way, and the way placement new was initially added for, is malloc. Right? So malloc is a C function that only allocates storage. It does not create any objects. So we can use placement new to explicitly start the lifetime and create our object with the appropriate value. And then we can use it. When we're done, we end the lifetime by calling destroy it, because you can't write tilde int. Right? And then we're freeing the memory and deallocating the storage. And now we're having full control over the entire lifecycle. We do every step of the object lifecycle completely by hand. A more C++ version would be to use operator new. So again, it's a global function that you can call, and it's sort of the C++ version of malloc. Right? It only allocates storage. It does not create any objects. And again, then we placement new, we use it, we destroy it, and we use operator delete to deallocate the storage. More interesting, we can use an array of unsigned chars.byte. So here we've got an array of unsigned char, suitably aligned, suitably big for an int, and then we create an int in there. This starts the lifetime of our int object, which we can use. We end the lifetime, and then we delocate the storage when we reach the closing brace, because it's automatic storage division. So this is really useful if you're implementing optional, for example, right? Then you just have a blob of bytes, and then you manually create the object in them. But you can also do this. You can reuse the memory of an existing object. So here we're creating an object using a definition. We then end its lifetime. At this point, we don't have an object. We just have a destroyed thing where an object used to be. So we manually start the lifetime with another int object in its place using its storage, which we can then use. And then we end the lifetime. Now there is something sketchy going on here, because which object is actually the lifetime ended, the first one or the second one? I'm getting a phone call from my dentist. Anyways, so there's something sketchy. Keep that in mind. But first of all, you have to be really careful when reusing memory. So for example, const is const. When you create a new object within storage that is const, that is undefined behavior, right? If we got a const int, we end its lifetime. This part is fine. But then we put a new object in there. And this would sort of change the value of a const thing. So this is undefined behavior. Const means const. So mostly. If it's on the heap, it's fine. So here we're creating a const int object on the heap. And then it's no problem. Const on the heap doesn't mean anything. We're free to use that. It only applies to static, thread, and automatic storage duration. You also, when you do that, the compiler is still going to destroy the object. Right? So when you manually end the lifetime, the compiler doesn't care. He's going to end the lifetime again. So when it has a non-trivial destructor, you will destroy it twice, which is undefined behavior. So when you do that, you have to be careful about putting something back in there before the scope ends. Now, let's look at this example in more detail. So we've got our object x, we destroy it, we create a new one. We then use the pointer returned from placement new. This is OK. Is this also OK? Can we just use x, right? Can we just reuse it? And the answer is sometimes. So if after the lifetime of an object has ended, a new object is created, a pointer that points to the original object, a reference that refers to the original object, and the name of the original object will automatically refer to the new object if the original object is transparently replaceable by the new object. When is an object transparently replaceable by the new object? The definition is very complicated, so I simplified it here. It's transparently replaceable if A and B use the same storage, which makes sense, and A and B have the same type. And then there are 3 exceptions. If one of them is a const object, then you cannot transparently replace it. If one of them is a base class, then you cannot transparently replace it. And if one of them is a no unique address member, then you can't transparently replace it. And when you deal with sub-objects, it recursively applies to the parent. What this means is that this code is perfectly fine. We're having an int object, and we're placing it with a new int object at the same location. This is a transparent replacement, so we can access x, just as if nothing has happened. And this is also why the closing brace, the compiler will implicitly destroy the original x object, which is fine because we did transparent replacement. Right? So this all works out. In a member function, this is technically also okay. Like we are destroying this and replacing it with a new one. This is transparent replacement, provided the foo object that we're doing it on is neither a base class nor no unique address member. Right? So like sometimes this is okay, but like there are some edge cases where this is a bad idea, and so you just shouldn't write code like this. But like this code is perfectly fine. Here we're doing it on like an individual member function, and like nobody else will even notice that we did it because we're dealing with transparent replacement. So when do we actually have non-transparent replacement? Well, for example, when we're replacing a const object. And remember, you can only do that on the heap. So we allocate our constant on the heap again. Then we do a non-transparent replacement because they're const. So using the new pointer is fine. Using the old pointer is undefined behavior. And the reason behind that is as follows. The compiler looks at the first line. So if you've got pointer, it points to a const int object. This means that star pointer can never change because const means const. Then in the third line, we're replacing it and changing its value because const doesn't really mean const when it's on the heap. But the compiler doesn't care about that. The compiler sees the star pointer in the last line and says, well, this must still be 11 because it points to a const object. Right? So this is why it's a non-transparent replacement. This is why this is undefined behavior. In practice, it will just print 11 instead of 42. Or maybe like in this code, the compiler might figure it out, but like in general, this is the idea. Now, for some reason, you really want to do this. Can you? And the answer is you can. You can use launder. Now, launder is a magic identity function. It takes a pointer, and it returns the pointer unchanged. But now the new pointer sort of tells the compiler, hey, you might have to reload its value. We're going to look at how it does that later on in the talk. So accessing the new pointer is fine, and accessing a laundered version of the old pointer is fine, because it tells the compiler, hey, the star pointer might have changed, please reload it. So this is OK. And standard launder even helps to prefer references. So again, we're having an object, we're having a reference to this object, we're doing a non-transparent replacement, accessing the reference as undefined behavior, but taking the address, laundering it, and dereferencing it is fine, because we laundered the address. So the compiler is forced to reload. Note that like launder isn't some magic get out of free card, right? Get out of jail free card. It does not prevent undefined behavior. So assuming floats and ints are the same size and alignment, then the third line is OK, where we like non-transparently replace our float object with a different int. We can then access the pointer, because we just have an int, all is good. We cannot access the float pointer, because we don't have a float, and we did a non-transparent replacement. So we cannot write star f pointer. And even if we launder, laundering doesn't help us, right? Because we still don't have a float. It's an int, not a float, so this is still undefined behavior. Launder doesn't help you there. So when do you need to use launder? Well, if you reuse the storage of like const heap objects, because otherwise you can't reuse it anyway, base classes or no unique address members. So never. We're going to circle back to that. Any pressing questions about placement new? OK. Now let's look at implicit object creation. Another tautology. An object is created by an operation that implicitly creates objects. And the idea behind that is the following code. You call malloc, you cast that to an int pointer, and you start using it. This should not be undefined behavior, because there's a lot of code that looks like this. Like essentially all C code looks like this, and if this is compiled under C++, this should not be undefined behavior. It would be undefined behavior under the if implicit object creation wasn't a thing, because like there isn't any rule, like at no point do we create an object, right? malloc doesn't create objects, and we just dereferencing it and start assigning it. Nobody has created an object. And so in C++20, we decided, yeah, maybe this shouldn't be undefined behavior, let's make this okay. And we added the rules for implicit object creation. So formally, some operations are specified as implicitly creating objects. And then they implicitly create objects, thank you, if it's an implicit lifetime type, and if doing so would result in the program having defined behavior. So essentially, if it helps you, the compiler creates objects for you. And this is, I think, the only instance where the C++ compiler goes out of its way to prevent undefined behavior for you. Right? Like, it looks at what you're doing, saying, hey, this would be undefined behavior, but I can help you out, so it's not gonna be. So what is an implicit lifetime type? This is the formal definition. It's a lot of words to say construction and destruction do nothing. If the type has a constructor that does something, right, then it will not implicitly call the constructor, because that would be weird, and also it wouldn't be implementable, as we can see. So what are those operations that implicitly create objects? Well, malloc, for starters. Any variants like realloc or calloc or whatever, operator new, allocation functions from the allocator, and a whole lot of other things, right? They all implicitly create objects. So the second alignment is okay, because the compiler, this would be undefined behavior, but malloc implicitly creates objects, so it will implicitly create an object to make your code okay. Anything that starts the lifetime of an unsigned char or stored byte array also can implicitly create objects. So we're having an unsigned char array, suitable aligned, suitable big, and then we are treating it as a pointer to an int, like its address as a pointer to an int, and then we start using it as if it were an int, so the compiler goes ahead and creates an int. Otherwise, this would be undefined behavior. But like it implicitly creates an int. Technically, this is still undefined behavior. Timo, are you here? Yeah, your paper fixes that. Is it your paper, or do you have the other paper? You might have the other paper.
No, mine is the start lifetime asking.
Yeah. I might give you. Okay, then you get a shout out later. But technically, we need to use a launder, because otherwise we don't actually get the address of an int object. This is just like a weird flaw in the wording. Like there's a paper in flight. This fixes it. I'm just gonna like hope it lands, because otherwise this is kind of useful. But like pretend the launder isn't there. It shouldn't be there, but like for now it has to be. Another operation that implicitly creates objects is the memcopy and memmove. It's a char buffer, not an unsigned char buffer, so it creates nothing. We then memcopy some int over there. This creates an int because we later lead an int, and memcopy is an operation that implicitly creates ints. And again, the launder is only necessary because of the same thing as previously, pretend it's not there. And then finally, there's a set of like implementation-defined operations like mmap or virtual alloc or something, right? So if you just mmap some memory and start using it as an int, that's okay, because the implementation probably makes it implicitly create objects for you. Now, how does the compiler actually know when to create objects and of what type? And the answer is easy. It uses time travel. So here we have an unsigned char buffer. And then we roll a dice, and we either assume it's an int or we assume it's a float. So initially, when we execute the line, no int, no float, anything. Then we start executing, and let's say the die is even, so we need an int. So the compiler says, oh, this would be undefined behavior. But I can implicitly create an int in this buffer. So I'm going to travel back in time and create an int in there. And from this point forward on, the buffer is an int, because it always has been an int. At no point did the buffer contain anything other than an int. Right? And if we then later go ahead and use it as a float, that's undefined behavior, because the buffer is an int. Right? It only does the time travel once. So essentially, every time, on the first use, if the compiler can, it will travel back in time to the appropriate point and implicitly create the object for you. Alternatively, you can have like a quantum mechanic situation where like the buffer contains both an int and a float, and then collapses as soon as you observe one. And this is also why the constructor must not do anything, because I've been told that like time travel isn't actually implementable. So if the constructor had side effects, then that would be observable, right? So it's purely just like wording for the abstract machine, and the actual CPU doesn't care about it, so it doesn't actually do anything. It's just like some trick to make this code well-defined. And again, implicit object creation isn't another magic undefined behavior removal thing, right? We're having an int, we reinterpret casting it as a float, and we're laundering it for good measure or whatever, right? This is still undefined behavior because we're having an int, we don't have a float, and we don't implicitly create an int because we didn't do any of those operations that implicitly create objects. Now consider some code like this. We're having some function that takes some buffer, and we've got some data, and let's say the buffer came from the network, and we know that the other side put in the data. Then we can just start using it as if it were like an appropriate data buffer. And if buffer came from an operation that implicitly creates objects, at the use, the compiler will travel back in time and implicitly create objects. But if buffer came from an operation that does not implicitly create objects, then this might be undefined behavior because we don't have anything to time travel back to. So at this point, we need to do something different. What we could do is like placement new. Just like placement new, something over there, data doesn't have a constructor, so this doesn't actually do anything. Unfortunately, placement new logically changes the value, even if the constructor doesn't do anything. Right? It still starts a new object with entirely different values, so this might be can change the values, even though it probably doesn't, but like formally it does. Now, what we need is some way to tell the compiler, hey, this is my buffer. I want to like implicitly create an object in there, but I'm not sure whether you do it, so I want to implicitly create an object. And for that, we can use start lifetime as. So start lifetime as takes our buffer, we say the type, and now the compiler goes ahead, and when we start using it, it says, I can use start lifetime as to implicitly create an object, so I'm going to do that. This doesn't change any of the values, and it's all good. And there's also one version that takes like a pointer and a count, and it creates an array of data objects. So this is how you implicitly create an object without touching any of the bytes. Because a lot of you probably write code like this, and like this might be technically undefined behavior. So if you want to be fully conforming, you have to use start lifetime as. In practice, start lifetime as is like a C++23 feature that I don't think has been implemented. So, do whatever you have to, but, just funding that up. And we can actually sort of implement start lifetime as yourself by using a memmove of pointer to pointer, like essentially just moving the pointer to itself. This doesn't actually copy any of the bytes, but memmove is an operation that implicitly creates objects. So when we later then need an object, we can time travel back here and create our T. So this is like a very crude approximation of start lifetime as, and the standard library implementation probably uses some compiler build-in that is an actual no-op and also works for const. So this is how we can like create objects out of thin air without actually running any destructors, constructors. Now, when do we like implicitly destroy an object? Because we've got implicit construction, we've also got implicit destruction. So the lifetime of an object ends when the object is destroyed, or the destructor call starts, or the storage is released or reused. So when we go back to the code from the previous level, we have an end x, and then we call placement new. This reuses the storage of our x object, so it ends the lifetime of x and starts the lifetime of a new one. Right? So this both ends the lifetime and starts the lifetime because we reuse the storage. Similarly, when we create our buffer, this starts the lifetime of an unsigned char array. And then when we placement new over it, this ends the lifetime of the unsigned char array and starts the lifetime of the int. And then we can use the int. And that also means that like memory leaks are not undefined behavior. Right? So we've got a string, then we end its lifetime and create a new one. This is perfectly fine. We just don't run the destructor, so we just have a memory leak. But we still destroy the object, just we end the lifetime by not destroying the object. Sorry. It's just a memory leak. It's not undefined behavior. It's just a bug, but like the standard doesn't care. Right? And then again, because of transference replacement, when we destroy the actual thing. Any urgent questions at this point?
Why do we use unsigned char arrays instead of standard byte arrays?
I'm using unsigned char array instead of stood byte arrays because unsigned char is more to type, and I didn't hit my. I had no particular reasons. I just used unsigned char arrays. Yeah. Okay. Now let's look at provenance. Hannah talked about provenance in the keynote, but like it's a really important thing. Consider this code. We have some variables x and y. We set y to 11. Then we do something with the address of x, and then we return y. The compiler looks at this code, and the compiler looks like on a function by function level, and it sees that y is 11, then we don't change it, so return y, optimize that to return 11. But what if this is the definition of do something? Right? So do something takes the pointer, offsets it by 1, and sets it to 42. And let's say that happens to be the address of y. Right? Then this optimization would not be okay, because now y would be 42, and we aren't allowed to return 11. But maybe you say, okay, but like there's no guarantee that this is the case, right? There's no guarantee that like pointer plus 1 is the address of y. Well, what if we make that guarantee? So we put in an if. So like if the address of x plus 1 equals the address of y, then we're going to pass the address of x to do something, which goes to x plus 1, sets that to 42, which now modifies y. Because every time we execute the statement, we know that that is the address of y. So we sort of change y. But the compiler is still going to optimize it away to return to 11. Right? Because the compiler just looks at foo. It doesn't care about do something. Right? And it sees y isn't modified, so it can return that to 11. Like, so there has to be some undefined behavior in there. And where's the undefined behavior? Right? Because pointer plus 1 is the address of y. Right? To be allowed to modify that. They are the same address. But pointers aren't just addresses. And crucially, just because two pointers are equal doesn't mean that they point to the same object. And because of provenance. So logically, a pointer is both the address and the provenance. And the address is the only thing that is physically observable. That is the thing stored in the CPU. But provenance sort of identifies the object or allocation the pointer was derived from. Like it's a semantic property that's only relevant in the formal model. And when we dereference a pointer, that is only valid if the address is in the range of the allowed addresses for that particular provenance, and the current provenance of that address is the same as the provenance of the pointer. And crucially, pointer provenance does not change using pointer arithmetic. So in this code, the dereference is not okay because pointer is the provenance of x, and pointer plus 1 isn't a valid address in the range of x. So even though it is the same physical address of y, it has a different provenance, so the dereference is undefined behavior. And that way, the compiler is allowed to optimize this code. Right? It's like a pretty useful property to have, but it also means that you can't just do arbitrary pointer arithmetic with pointers and just modify memory through there. And with provenance, we can also understand non-transparent replacement. So when we've got our const int object, which we then destroy and then put in a new one, this is now a pointer to a different provenance. Right? So new pointer has provenance b. So when we dereference, that is fine, because the object there also has provenance b. But the dereference of the original pointer is undefined behavior, because that one still has provenance a, and we no longer have an object at that address with provenance a, we have an object with provenance b. And when we launder it, launder returns the same pointer, but it only keeps the address the same. It magically updates the provenance. So the result of launder is a pointer that now is the correct provenance, because it sort of magically updates the provenance to whatever is the provenance of that address. Right? So this is what launder does, and this is why this code is okay. And it's not just pointers that have provenance, reference have provenances too. So when we do the code with the reference, this is undefined behavior, because the reference now is the wrong provenance, but when we launder the address and dereferencing it, we get a pointer with the correct provenance, so this is fine. So every object has a unique provenance, and all objects in an array have the same provenance. This allows you to do pointer arithmetic from like one part of the array to the next one. And when we reuse the memory of an object, this changes the provenance unless it is transparent replacement. So if you do transparent replacement, then the provenance stays the same, so all the pointers keep being valid. But if you do a non-transparent replacement, then this is undefined behavior. And if you want to update it, you use .launder to update the provenance of an object. Now that we know about provenance, we can apply that knowledge to type panning. So generally in type panning, you have some bytes stored in an object of type t, t1, and you want to interpret it as an object of type t2. And what you know, you can't just do reinterpret cast. So reinterpret cast, like from the int to the float, is undefined behavior, so we can't do that. Except the reinterpret cast is actually fine. It's the dereference that's the problem. Right? So the rule behind that is the strict aliasing rule, and like the sort of colloquial, you say that you can't reinterpret cast between unrelated types. But that is fine. That is not quite correct. The accurate phrasing is the access is undefined behavior. So when you access a stored value of an object through some L value whose type is not similar to the dynamic type of the object, then that is undefined behavior. So you can't access an object through a pointer of an unrelated type, but you're free to create the pointer to the unrelated type. Because in general, the type of a pointer or reference is only really relevant when accessing the referred object. So if you want to, you can store all pointers as int pointers, right? As long as you reinterpret cast appropriately every time you dereference, it's perfectly fine. It's just horrible code, but like the type of a pointer or reference doesn't matter. Unless when you access or when you do pointer arithmetic, because then it increments by size of, but you know. Now there are a couple exceptions to the strict aliasing rule. So it either has to be like the correct type, or a signed or unsigned type, or char, unsigned char, or byte. So when we have our int, the first line is okay, because unsigned is like the unsigned version of int. So we can sort of don't violate the strict aliasing rule. I don't know why this exception is there, but it is. This code is okay. And also you can use char, unsigned char, .byte, and this time I'm using .byte to do this. And the idea behind that is that you can sort of like access the object representation, so the sequence of bytes of an object in memory. So when we got our object and we reinterpret cast to a byte pointer, we can then sort of iterate over the bytes in order to print the stuff. And this is the point where I give a shout out to Timo now, right? Because in theory, this is okay. This is the intent. But this sort of was like undefined behavior because it's like there's a bug in the standard, it got accidentally broken. The bug in there is that like we're doing pointer arithmetic, but at no point do we have an array of bytes. We have a sequence of bytes, which isn't an array, so we can't do pointer arithmetic. And this is where Timo has a paper, correct? Yeah. So just the intent is this to be okay. It's not currently that it's being worked on. Now, when we can't reinterpret cast, maybe we can use placement new. We can't use placement new either. Because again, placement new sort of changes the value, right? It starts in a slightly new float, and like logically, this has a different value, right? And also, we can't then access the old one because we like ended the lifetime of the int object. Now again, using placement new, you have to be really careful about getting the pointer. So in this code, we are creating an int object, we reinterpret casting it to a float pointer, and then we're placement newing on there. The dereferencing of the float pointer is still undefined behavior. Even though we're having a pointer to float, and we're having a float at that address, we cannot access this at the float, because the float pointer is the provenance of the int. Right? Just because a pointer has the correct type, and it points to the location where we have an object of that type, we might not necessarily dereferencing it, because the pointer sort of has the wrong history. Right? F pointer is still a pointer to int, even though it's a pointer to float. Right? And even if you do it afterwards, that doesn't help you. F pointer still has the provenance of the int object, can't dereferencing it, wrong type. Well, wrong provenance. Correct type, wrong provenance. So you either have to use the pointer from placement new, or use launder to update the provenance, right? So have to be really careful when you do this sort of thing. The pointer sort of remembered where it came from. The provenance matters. You have to be a lookout for that. And this sort of rule is also what applies to unsigned char. So this code is undefined behavior, because the int pointer is logically still a pointer to an unsigned char array. And when we access it as an int, this is undefined behavior. And like even though implicit lifetime creation would kick in, the pointer is still a pointer to an unsigned char array. This is where this paper comes in. I consider this a bug, but right now you still need to use launder to get the correct performance. So when do you need to use launder? When you want to reuse the storage of const heap objects, base classes, or now unique address members, or when you reuse the memory as storage for a different type, and in order to work around this bug. So in practice, still never, but there are some terms and conditions that might happen. Now, type punning with start lifetime as works. It's weird, but it works. So we've got our int, we start the lifetime of the float object. Then we can use it. This is perfectly fine. It will create a float object without touching the bytes, so now we have a float. It's just a bit odd way to do type punning because we no longer have an int, right? This ended the lifetime of the int object, right? What we can sort of do is we can then afterwards start the lifetime of an int to sort of like type pun it back, but then we can no longer access the I object because we've changed the provenance when we go into a float, And when we then went back to an int, we changed the provenance again instead of going back to the original provenance. So the I pointer is now still points to the int that used to be there and not the current int, as if you launder it. But technically, this works. It's just not really useful. So the actual way to do type panning is you can use memcopy, because memcopy sort of sidesteps the entire lifetime thing. We've got an int object, we have a float object, and we just make the bytes identical. Right? Then we don't have to deal with any object lifetime, any launder, it just works. The more modern version is bitcast. Bitcast is a compiler intrinsic that just says, hey, I'm doing type panning, so please don't actually create a copy. And now it's perfectly fine. There's a weird exception for type panning. So when you have a struct of standard layout with a member, you can sort of take the address of the struct and reinterpret cars to the type of the first member, and then you can access the first member. And then you can also go back to the struct. Right? So sort of the struct and the first member have the same provenance, so you can sort of reinterpret cars between them. This is sometimes useful, and this is sort of how you would sort of fake inheritance if you don't want to use inheritance. Like you can have a derived struct with as a base as the first member, and then they can reinterpret cars between them. But you would just use inheritance. So formally, it says two objects are pointer interconvertible if then they have the same address, and you can use reinterpret cast. And the pointer interconvertible if they're the same object. Also, if they are a union object and one is a member, so from a union member you can go to the union, and from a union you can go to any union member, but you can't go from one union member to the other union member, you have to go by the union first. Oh, no, never mind, it's transitive. Sorry. I've given this talk a lot and I sort of forgot it. Anyways, and if one is a standard layout class and the other is the first non-static data member, then that is also fine. That is the example that we see, and it's transitive. So you can go from one union member to the other union member because you would go by the union. And this is also where the paper about launder of the unsigned char array would add their fix to say an unsigned char array is interconvertible to any object that lives in its storage. What you also can do with type panning is you use a union. So the final place where objects are created is when you implicitly change the active member of a union. So if you've got the union of an int and a float, it's initially an int, then we change it to a float, and this ends the lifetime of the int object, starts the lifetime of a float object, because the assignment creates a new object that reuses the storage of the int object. So we end the lifetime. So now we can access the float, but we can no longer access the int, because the int was destroyed by the assignment. In C++, you cannot do type panning via union. You can in C. There is an exception for that. It's called the common initial sequence. So when you have a union with types T1 and T2, and both of them have common initial members, then you can access them through either one. In code, this looks like this. So we've got a union, struct A, struct B. They both have a prefix member, and then we can access the prefix member by either doing u.a.prefix or u.b.prefix. So this is fine. So to conclude, some guidelines, because those were a lot of what does the standard say? What does it mean for you now? Don't rely on implicit object creation. It's weird, it's vague, don't do it. It's nice to have, but you shouldn't rely on it. Use placement new to explicitly create a new object when you don't care about the value, and use start lifetime as if you care about the bytes. So you have some bytes, call start lifetime as to get an object in there. And don't rely on implicit object creation, it's very subtle. Whenever possible, use the pointer from placement new and start lifetime as directly. That pointer has the correct provenance. Right? Then you don't have to bother with launder. And instead of using unsigned char buffers or .byte buffers, use a union. If you use a union, then you also don't have to bother with launder, you don't have to bother with placement new in many cases, right? You can just implicitly go from one to the other. So I'm going to be sneaky. Since this is the last talk and I'm going to stick around for questions, I'm instead going to talk about zombie pointers for my final 5 minutes. So the standard says, before the lifetime of an object gets started and after the lifetime is ended, any pointer may be used only in limited ways, and similarly for references. So we've got an int object, we destroy it. We can still take its address. We can still bind references. We can take more addresses. We can do. We can. Why does this say OK? This shouldn't say OK. Oh. Oh yeah, this is okay because it binds a reference, I think. Okay, maybe not. I have to double check. I haven't used the bonus slides a lot. Anyways, and you can compare the pointers. Similarly, in code like this, so we've got an object, it's destroyed, but then like the actual reading is undefined behavior, and the actual dereference of a pointer into an object is undefined behavior, right? Because we're accessing it outside the lifetime. So we have undefined behavior if such a pointer reference is used to access the value of an object, to call a non-static data member of an object, or to delete the object. And anything to do with virtual base classes or dynamic cast also cannot be done outside the lifetime of an object. But there's something different. There's access outside the storage. So after the storage, which the object will occupy, has been allocated, and before the storage has been reused or released, any pointer can only be used in limited ways. And similarly, any reference can be only limited in limited ways. And this is related to the pointer lifetime end zap. So when you're at the end of the duration of a region of storage, all pointers that represent the address of any part of the region of their storage become invalid pointers, which you can no longer dereference, you can no longer deallocate, and any other use has implementation-defined behavior. So we've got some code. We create an object, we destroy it. The dereference is undefined behavior, but the comparison with null pointer is okay, because the storage is still okay. Right? It's like it only destroyed at the closing brace. But when we use new and delete, now we delete and deallocate the storage. Then the dereference is still undefined behavior, but the comparison with null pointer is implementation defined. Because pointer is a pointer that points to deallocated storage. And in particular, this might return true. Because it is implementation defined behavior, and you could have an implementation that is like really nice and sets pointer to null pointer when they're deleted. Now this has consequences, with especially like multi-threaded code. So this is a very simple stack implementation. So we have a pointer to the top node, and then in push, we sort of like do a compare exchange to like put in the new node in the top. And then we've got a function pop all, which simply removes it from the stack, and then you just have a pointer that you can manually follow. Now what we can do is we can write code that leads to an invalid pointer. So let's say top points to node 1 with provenance A. Then that T1 starts executing and allocates a node T at address B. It sets the old top to node 1 in line A, and updates the next pointer of node 2 to already point to node 1. Then it gets interrupted, and another thread goes in, does pop all, and deletes node 1, and delocates the storage. Then 31 does the compare exchange weak, which is now implementation defined, because we're compare exchange reading the old top pointer, which points to the allocated storage. This is implementation defined behavior. So in particular, the compare exchange weak may or may not succeed. But something even worse can happen. Let's say now we're at this point, thread T2 deletes node 1, and now we allocate node 3, which reuses the location of node 1. And then we execute the compare exchange weak, which is implementation defined. And now something really subtle can happen. Because what is the result of the comparison? If the comparison returns true, because the addresses are the same, then node 2's next pointer has the wrong provenance. Right? We're just going to have node 2 still point to node 1 at provenance A, so you can no longer go through the list because it does not point to node 3, it points to the deleted node 1. But if the comparison returns false because the provenance is different, that's not implementable, because like provenance doesn't actually exist in the hardware. Right? So this is a bug in the C++ standard. And like SG1 has been working on solutions for it for like 20 years, 25 years, something like that. Like, there are like some proposed solutions by like making the comparison meaningful and like implicitly picking provenances or whatever. It's like a whole open problem that we've been working on. And on this kind of depressing note, I want to end. I work at ThinkCell. We do a great job. You don't have to know any of the contents in this talk to work for us, but we're hiring. Thank you. And I do have socks. So like, come by and grab those socks. Thank you. Yeah. Yeah, I think like we're out of, but like I'm gonna be here, just maybe like outside the room or something. You can ask questions there. So, thank you, and come and grab socks before you go.